All right, so we've got ourselves a pretty important lesson here. We're finally going to learn for real how you solve exponential equations. And I've kind of pointed out examples like this in several videos in a row right now. Right now, with exponential equations, sometimes we get lucky and we can just guess our way to getting the right answer. But sometimes we can't do that, and we have to just guess and check with decimals using technology to help us. We're going to learn two methods in this video for solving exponentials. And basically, after you learn these two methods, you can tackle any kind of exponential problem I throw at you, whether it's one like this or one like this. So let's go ahead and get to it with our first method. I'm going to give you the name for this method in just a minute here, but I want you to think if you can solve this first equation on your own using common sense. So instructions are going to say just to solve for x. So use common sense and see if you can figure out how to get the answer to this first question. Now, what I would be looking for from you in this problem is you would look at this problem and say, well, there's a 7 over here. There's a 7 on this side as well. And the problem is equal, so the two sides must be the same. The only way that could be true, since they're both a base of 7, is if this exponent is actually the same thing as this exponent right here. Logically, if the 7's are the same and it's equal, the exponents must be the same as well. So what I'm essentially allowed to do on this first example here is totally disregard the fact that this is exponential. Well, that has to equal that. And then I'm back in easy Algebra 1 classroom. I can just go ahead and get x by itself pretty straightforward here. Add that 4 over as well. So I'm going to get negative 4 equals 2x. And I get my answer of negative 2. And that is the correct answer to this problem here. If you plug in a negative 2, you're going to get 7 to the, that'd be negative 14, equals 7 to the negative 14. So it is the same on both sides when you use this x. So this method right here is going to be called the common bases method. If your bases are the same, you just need to equal your exponents and you're done. Really straightforward. Now you may ask yourself, well, okay, fine, but like what if it's not the same number? Like on this second example here. If you have a 2 on one side and an 8 on the other side, you're not going to be able to just set those exponents equal because that won't be true anymore. There is a way to manipulate this problem so that you do end up with the same base. And pause me and give it some thoughts. This is something where kids have a lot of different ideas, but only a handful end up getting the correct idea. So you can test yourself here and ponder what you could do to make it into the same problem. Now, I will hear a couple pretty common wrong answers when I ask kids about this. I'll have kids say things like, well, why don't you multiply by 4? Because if you do like a times 4 over here, that'll be an 8. If you were thinking something along those lines, it's a good thought, but you're wrong for a couple of reasons. First of all, I could not even multiply this 4 to the 2 because 2 already has an exponent on it. So I'm not allowed to make that an 8. And even if I somehow could, you have to remember you would have to do the same thing to both sides. So you'd end up doing a 4 over there, and it's definitely not going to be the same anymore. So doing something like multiplying by 4, not going to work for me. If you say like, oh, divide this by 3, well, you can't do that anyway. But then you'd have to do it over here as well. So it's kind of weird because if you do something to one side, you have to do that same thing on the other side. The exception to that is what we end up doing for the solution here, which is to use substitution. Somewhere, even if you weren't able to figure out the right answer to this problem, a lot of kids realize, oh, 2 to the third is the same thing as 8. So that's going to somehow have to play into what we do. And actually, what I'm going to do here is I am going to sub in a 2 to the third in place of the 8. Because 2 to the third and 8 are the same thing. I'm not messing with the equation. I'm just plugging in one thing that's equal to another. I'll have a lot of kids who will try to put a third power over here on the 2. But if you put a third power here, you have to put it there as well. That doesn't work out right because you're changing 2 to something else. But this side is okay because 8 really already equals 2 to the third power. So what is this problem going to look like now? Well, my left side, not going to change. Still looks like this. My exponent over here, not going to change. The only thing that changes is where it used to say 8s, now I'm going to sub in a 2 to the third, because 2 to the third is the same thing as 8s. Well, now what I can do is I can distribute these exponents out, clean this up a little bit. I'm going to have 2 to the 7x plus 5 on the left, and my right side is going to say 2, and that's going to make a 6x minus 9. So basically, I did a clever substitution. I realized, oh, that's 2 to the third. Now my bases actually are the same thing. I have a 2 here, and I have a 2 here. So what I can go ahead and do now is equal these exponents to each other, and I'm just doing easy math to finish this one off. So I got 7x plus 5 equals 6x minus 9. If I solve this, it looks like I'm going to get the answer of negative 14. You can plug it back in to make sure it works, but it totally will. That is our solution to that second problem. So why don't you go ahead and see if you can handle this third problem for yourself. I'm going to give you a hint right here. This side, the weird side, you're going to try to turn it in to match the plain 3 over here. Generally, you take the crazier side and try to make it look like the nicer side. So figure out 1 over 243 is the same thing as 3 to what power? And that's your job right now. So after a little bit of thought, you hopefully were able to arrive at the fact 3 to the 5th is 243, so 3 to the negative 5th is what we'd be looking for right here. So I'm going to sub out that fraction, and I'm going to sub in a thing with a 3 so it will match with the right side. So it's going to say 3 to the negative 5th, and then the rest of the problem does not get influenced at all so far. It's going to look like this. Well, once I'm at this point, I can go ahead and distribute my exponent. It's going to say 3, and it's going to be negative 10x minus 20. And then I'm going to have 3 to the x minus 6. And now I'm just doing easy math, equaling my exponents, finishing it off. If you equal your exponents to each other, I'm going to have an 11x and a negative 14. You're going to get negative 14 over 11, it looks like, for your solution. So make the bases be the same, set your exponents equal. We've got one more of this style, and this one is a little bit tougher in the sense that when you do one of these questions, sometimes, like the last two, you can get away with only changing one of the two sides. That's what I did in the second and third examples. This problem, working with a base of a 0.2 or a 625, it's not impossible, but it's just one big mess. Neither of those is a really nice base, like a 3 or like a 2 on my last problem. So what I do on this example, first of all, I'm going to realize that a 0.2 is the same thing as 1/5. Then what I'm going to do is I'm going to ask myself, 1/5 and 625 are part of what exponent family? And it turns out they are both part of the 5 exponent family. So I'm going to manipulate actually both sides of this problem so I can get a clean base of 5, and then it'll be easier to work with. Trying to deal with a 1/5 or a 625 for matching bases is just a lot more work. Well, 1/5 is the same thing as 5 to the negative first. So that's going to be my left side. I'm going to do a 5 to the negative first. And 625 is the same thing. I'm going to sub in a 5 to the 4th power. Now my setup looks like this, and I can go ahead and just do easy math, drop my bases, and I'm going to go ahead and solve this guy for x. If you do that, you're going to get, it looks like 25 over, is it a negative 16? Yeah, negative 25 over 16 for your answer. When you actually go and you would add the 1, subtract, blah, blah, blah. You guys know how to solve math. So negative 25 over 16 is our solution. These types of problems aren't so bad. They just rely on knowing your power families. And most of the time, you can turn them to be matching bases somewhere between 2 and 10. So if you know your power families, you're going to be in good shape. That takes us to our second style of problem. And our second style of problem, unfortunately, is not going to work out as cleanly as the ones we just did. Sometimes, oh my gosh, why is this line coming back? Sometimes, no matter how hard you try, you aren't going to be able to make the bases into the same number. 7 and 200 just aren't parts of the same power family, no matter how hard you want them to be. So, we need a different strategy. Method 2 is going to be using, oh my goodness, why does that keep coming back, guys? It's frustrating. Method 2 is going to be using the log stuff that we've been learning about in the past couple lessons. So method 2 uses logs. Now, the idea for this problem here, we have learned that as long as you do something to both sides of the problem, you're okay. I can add to both sides, subtract, I can do exponents to both sides, I can do radicals to both sides. As long as I'm consistent and I do it to both sides, I'm good. Well, I can also choose to take the log of both sides of this problem. So what I'm going to do is take the log of 7 to the x and take the log of 200. I basically throw down a log to this side and to this side over here. Okay? Now that's great. It may be like, why this looks like more complicated. Why do you do that? It's great because we learned a third property of logs in the last lesson, which says that if you have an exponent inside a log, you're actually allowed to drag that number out of the log and put it out front. So in my original problem, x is sort of laughing at us right here. He's laughing at us because we can't get him by himself because he's up here in the exponent and we can't get him out of there. Well, it turns out if you take the log of both sides, that third exponent property lets us drag the exponent to the front of the problem. Now my problem just says x times log 7 equals log 200. Now this right here, this log 7 and this log 200, they're just decimals. I don't know what they are, but my calculator totally does. To get x by itself, I'm going to divide by log 7 to both sides. When I do that, these will cancel. Now, I don't have a property for dividing logs. We learned that in the last lesson. There's no clean way to do that, but I can type it in my calculator, and the calculator can give me an answer. So what I would do is I would just type in the calculator log of 200 divided by log of 7. And it's going to be important when you type this in the calculator that you remember to close your parentheses on the logs. That does make a difference here. If I type that in the calculator, I get 2.72 for my answer. So that means x is going to equal 2.72. And that decimal did keep on going, but I'm going to go ahead and round it just a bit. Okay? So before, my only option here would be just guess and check. Try different decimals. Just keep on trying till I make a 200. But if you use logs to solve it, you get the exact answer without the guesswork. If I wanted to verify, oh, did this work? I could try 7 to the 2.72 power. And you'll notice that's not 200 like it's supposed to be. But it's because I chopped this decimal off. I only did 2.72. If I do 7 to that full decimal, which is an irrational number, it keeps on going even past what the calculator shows, then you get the nice 200 like you're supposed to. Now, before I do the next example, this is one way you can solve with logs by doing what's called the common logarithm to both sides. There is actually a second option that you might like even a little better. So I'm going to rewrite the same problem before I go to the next one here. When I was in high school, so even like 10, 15 years ago now, you couldn't type other logs in the calculator. The only thing you could type in the calculator is a regular common log base 10. So this right here on the left is what I had to do when I was in high school. But your calculators are nicer than mine were when I was in school. And you actually have the ability to do a different log to both sides. Instead of just doing a regular common log like right here, you could actually choose to do a log with a matching base of 7 to both sides. So if you do that, that looks a little crowded right there. So I'm going to rewrite it. It's going to say log base 7, and this was 7 to the x, equals log base 7 of 200. This part right here is going to cancel. We learned that property earlier on, where if the base matches this base, they're going to cancel. X is by itself. So instead of doing a common log to both sides, I just saw, oh, I'm just going to cancel that 7 and do a log base 7 to both sides instead. I just need to type this guy into my calculator. And if I do that, what you're going to see, remember that button is in the math menu. You have to go down to log base. If I do log base 7 of 200, it's going to get me the right answer right away. Same thing I got earlier, 2.72, without doing that extra pull down the exponent and divide step. So it is going to be up to you which of these two methods you like more. Honestly, I'd like it if you could recognize both of them, but you can just pick the way that appeals to you. Let's go ahead and try out this next example. So on our next problem, I see that there is a 13 underneath my x. My x is over here. I'm trying to get him by himself. This 13 is messing things up for me. So what I'm going to do is toss down a log to both sides. I'm going to take the log of both sides. But instead of just picking a common log and having to do the drag down the exponent stuff like over here, I'm going to be smart about it. And I'm going to pick log base 13 because these will wipe each other out. And I'm just going to get a 2x minus 5. So you pick the base that you're trying to cancel. And all that's left is your exponents. So I also need to do the same thing on the other side. So that's just going to be button pushing on my calculator. I'm going to go log base 13 of that big number. So log base 13, and I have 857,000. That equals about 5.326. I'm going to do a couple decimal spots there. Well, now I'm just doing regular math to finish off this problem. I'm going to add 5 over. Now I got 2x equals 10.326, and I just divide by 2 to get my final answer. When you do this in the calculator, use the full number. So I'm going to do plus 5. Now it's that full 10-point number divided by 2. 5.163 would be my solution. So a log is one of the keys. I already forgot what I said. 5 points. Oh, it's gone. That's so sad. Sorry, guys. 326-ish divided by 2. 5.163-ish. All right, so I'll write it down, then I'll talk. Okay, so a log is a tool that we use to solve exponentials. It helps us get x out of the exponent and get our solution. We're going to finish with one final example that's a little bit uglier in the sense that I have variables on both sides of the problem. So that is going to make things a little less nice for me here. This was a 2x minus 9. So in a situation like this, you can't make them the same base. 5 and 8.3 is just not going to work out. You're just going to pick one of the bases to cancel out. You have to be consistent and do the same thing to both sides. So I could do a log with a base of 5 to both sides, or I could do a log with a base of 8.3. It doesn't matter which one you choose, but you have to be consistent. Just to show you guys that decimal bases are all right, I'm going to do a log base 8.3. You could just have easily done log base 5 to both sides, but they have to match. The way that I set this up, this side is going to work out nice. That will just say 2x minus 9. Over here on this side, that's not going to work out so good. I got to type it in the calculator. So I have to do a log base 8.3 of 5. So what I'm going to get is 0.7605-ish. So I have 0.7605 from doing that part. But that is going to get multiplied by this exponent of x plus 3. So what I've got going on right here, this is a decimal. I have to distribute that decimal to my exponent here. So this is working out a little bit gross. So when I distribute that, it's going to say 0.7605x plus, and then I just need to keep going, doing easy math, but with gross decimals. So that's 2.281-ish. 2.281-ish equals 2x minus 9. And then you just keep going and just do painful math with decimals, but not hard math. It's good to keep the full decimals for as long as you are able, but if you're getting confused as you're going through these, I won't freak out if you just give me like a handful of decimal spots here. That number needs to get added 9. That's going to make 11.281. And then on the other side, I've got 2 minus the 0.76 decimal, which I've got the full thing up there. So 1.239x. And lastly, I'll divide to get my answer, again, using the full decimal whenever I have the ability to do so. So I want my 11 number divided by my 1.23 number, and my final answer is about 9.102. All right. So 2 methods you can use for solving exponentials. The log method takes a little bit, it's a little more work, a little more tedious to set up when you're doing it, but sometimes you have no choice. So generally, you're going to look to see if the bases match, like a problem like this, because this isn't as bad. And if they don't, and there's no way to make them match, you can use logs to get your solution.